Hi everybody, my name is Sebastian Castro and I am the team lead for Group 16. My team and I will be discussing processing encrypted data today. The team members are as follows: myself, Jack, Griffin, and Adasia. I'd like to take a moment to discuss the contents of the presentation. We'll kick it off by talking about the problem statement and contributions, which entices HTTPS, data breaches, and data protection security protocols taken today. Then we'll briefly talk about homomorphic encryption. Going into our background materials, why is it called homomorphic, how and why that came to be. Then in the main body of our presentation, we'll give an overview of homomorphic encryption and dive into the three variants, including partially, somewhat, and fully homomorphic encryption. For fully homomorphic encryption, we'll dive into the 4 generations that have come to be, and we'll conclude the presentation by talking about impacts and challenges of homomorphic encryption today. And now we'll move on to the contributions slide. As for our contributions, our main target is to provide an extensive study of research papers and present it in such a way that our paper is easy to follow, organized, and can be used towards future studies of the topic at hand, and provide a reference for those wishing to venture even further into the contents of our paper and its presentation and the topic presented today. And now I'll pass it off to Griffin to start talking about data breaches.
These next 3 slides will show just how important fully homomorphic encryption is. We see here in the by the numbers figure that the number of records stolen in the year 2020 alone reached 1.245 billion. We also see that almost 50% of people in the United States were impacted by data breaches in the same year, as well as the time it takes a company to identify that a data breach has even occurred. Only a couple of days ago, Robinhood, which is a trading and investing app, experienced a data breach where approximately 5 million people had their emails shared, 2 million had their full names released, and roughly 310 users had their name, date of birth, and zip code, and of these 310, about 5% had even more of their data revealed. At this time, it is believed that no bank account or security numbers have been compromised. Still, a data breach like this should not occur. This slide just reinforces the importance of end-to-end encryption. Here we get a visual representation of the dramatic increase in the number of stolen personal records from 2004 all the way to 2019. Hypertext Transfer Protocol Secure, otherwise known as HTTPS, is the most used communication protocol on the internet, according to w3text.com. As of November 10th, 2021, HTTPS is used by default in 76.7% of the websites. HTTPS provides privacy and integrity of the exchange data. However, to process users' input, the data must be decrypted on the server. Moreover, most of the services store users' information in files in decrypted form, which can be compromised or used by the companies providing the services without the user's consent. And so, to guarantee complete user confidentiality, the data stored on the server end or in the cloud must be encrypted, and at the same time, the server itself should not be able to decrypt it. The HTTPS standard for securing online data is the most secure and efficient method to date. Currently, data breaches are rising at a rapid rate and show no signs of slowing down, previously shown in slides. The incremental increase in data breaches means that people are at risk of having their data stolen. To reduce the amount of data breaches we have seen, fully homomorphic encryption should be implemented. This way, users will be able to trust that their data will not be compromised.
Hello everyone, this is Jack, and before we get into the overview of the homomorphic encryption schemes, let's try to understand what makes an encryption scheme homomorphic. In algebra, homomorphism is a transformation of one set into another set that preserves in the second set the relations between elements of the first. In homomorphic encryption scheme, ciphertext is a homomorphism of the plain text. On the next slides, we will go over an example of a simple homomorphic scheme and the encryption function used in the example is from the paper called On Data Banks and Privacy Homomorphisms. Consider two large prime numbers, p and q, and n a product of p and q, such that n is difficult to factor. Let our encryption scheme be a tuple x mod p and x mod q, where x is a plain text. For the sake of simplicity, we will choose small values and let p be 5 and q be 7. Then n is 35, and let's say we have two integers x1 and x2 that we want to encrypt. The encryption of x1 and x2 is obtained by plugging their values, 8 and 11, into the encryption function. So the ciphertext of 8 is equal to 3, 1, and the ciphertext of 11 is equal to 1, 4. Next, we will add two ciphertexts component-wise. So 3 plus 1 is 4, and 1 plus 4 is 5. To decrypt this sum, we'll find x between 0 and n, such that x mod 5 is 4, and x mod 7 is 5. We know a list of all integers that produce a remainder of 4 when divided by 5. And from all of these integers, only 19 mod 7 results a remainder of 5. So 19 must be a decryption of the sum. And indeed, if we add our initial x1 and x2, 8 plus 11 is 19. Continuing with the example, let's say practical application of our scheme. Let's say we encrypt x1 and x2 on a user device and store both encrypted variables on a remote server. Since p and q are not known to the server, decryption on a server is not feasible, well, given that n is large enough and difficult to factor. And then user asks the server to compute x1 plus x2. Server adds two corresponding ciphertexts and sends back an encryption of the result. Once the result is received on a user device, user then decrypts it and gets a plain text of the result. And so, we were able to add two integers on a remote server without ever revealing their values outside of our system. This is possible only because the encryption scheme we used is homomorphic. With the homomorphic encryption schemes, operations over ciphertexts produce results equivalent to the operations over plain text.
Hi everybody, I'll be talking about partially homomorphic encryption. I'll give you guys a basic rundown. It's called PHE for short, and we only have two operations, uniquely addition or multiplication. We can apply the same operation as many times as needed on the ciphertext. In terms of applications, it's not used as much in cloud computing, but it is used a lot in blockchain applications and the Internet of Things. More to follow in the next slide. Additionally, it is also used for improving data privacy in healthcare systems and financial services. Now I'll be diving into some advantages and disadvantages of PHE compared to its counterparts. For some advantages, we have less complexity of the scheme in general, and that is because we're only applying either multiplication or addition operations on the ciphertext. Hence, there's reduced overhead in the computations, it's easier to comprehend, and it's easier to use. However, it's a double-edged sword, because that means that the applications are limited, because the scheme is generally weaker. It's also still computationally expensive, and if we apply too many operations on the ciphertext, then the original text might not be recoverable. Now I'll pass it off to my teammate Griffin to explain somewhat homomorphic encryption.
SHE stands for somewhat homomorphic encryption. It is a foundation to fully homomorphic encryption in that it allows both multiplication and addition operations. It also has the advantage of ensuring data security. However, these types of schemes are overall less efficient than the previous described PHEs because the ciphertext grows too quickly and becomes too expensive. These are just two of many she schemes. We have the BGN, which stands for bone, go, and nism. In this scheme, we can use as many addition operations as we want, but are limited to only one multiplication operation. Then we have the polycracker scheme, which allows as many operations of either, but the ciphertext is growing at an exponential rate, so the depth at which you can do these operations is extremely limited before the encrypted cipher will become unreadable.
Fully homomorphic encryption, the basics. So fully homomorphic encryption is also called FHE, just for simplicity. It supports both addition and multiplication operations, which is good because it is used when cloud services want more functionality than just addition or subtraction. And finally, it allows unbounded number of homomorphic operations through bootstrapping. Advantages and disadvantages of FHE. So some of the pros includes that it allows data to be secure within untrustworthy environments because it can be worked on while it's still encrypted, which is really good. And it also has features that are usable without compromising the data's privacy. So again, that goes into allowing other things to work on and edit the data without having to decrypt it at all. Some cons includes lack of performance, unlike partial homomorphic encryption. Performance is unpredictable depending on security parameters, and operation performance time is unpredictable. So even though it is good for being edited without having to decrypt it, there is a very unpredictable window of FHE being able to perform.
On this slide, we show main FHE schemes on a timeline. The idea of homomorphic encryption was introduced in 1978 and was initially called privacy homomorphisms. But the first fully homomorphic encryption scheme was described only in 2009 by Craig Gentry in his dissertation and research article called Fully Homomorphic Encryption Using Ideal Lattices. After that, several improved FHE schemes were developed, and all currently known major FHE schemes can be classified into 4 branches and 4 generations. We'll look at some of them in the following slides. As mentioned previously, the first fully homomorphic encryption scheme was developed by Craig Gentry in 2009. Gentry's first scheme is based on somewhat homomorphic encryption scheme, which was modified to allow bootstrapping, and more on that on the next slide. In this scheme, plain text are single bits, so zeros and ones, and the scheme itself allows 2 operation over ciphertext: addition mode 2, which is XOR, and multiplication mode 2, which is AND. XOR and AND operations allow execution of all possible Boolean circuits, though the main problem Gentry had to find a solution for is an exponential accumulation of noise after each multiplication. Since the scheme is probabilistic, it involves randomness, and each encryption has a noise. Once the noise of the ciphertext passes a certain threshold, its core decryption is impossible. But Gentry found an elegant way of reducing this noise. It's called bootstrapping. I will explain the process of bootstrapping using this diagram. Suppose we have a plain text X, encrypted homomorphically using a purple key. Initially, the ciphertext has a certain low level of noise, but after performing some AND or XOR operations, we have X prime with the noise level right below the threshold. At this point, we must reduce the noise if we want to guarantee correct decryption. To do so, we use another orange key to homomorphically encrypt X prime second time. Since both encryptions are homomorphic, we can use purple key to decrypt X prime inside the orange key. As the result, we then have X prime encrypted under the orange key with the low noise level. And so we successfully reduced the noise of the ciphertext. Theoretically, since Gentry scheme allows both addition and multiplication, it can be used to perform any kind of operations. And bootstrapping enables unlimited number of such operations, because each time the noise of the ciphertext reaches the threshold, it can be reduced using another key. But in practice, both multiplication and bootstrapping are so slow that the scheme took up to 30 minutes to process one bit, which makes it practically unusable. But the main contribution of the Gentry scheme is that it proved the very existence and possibility of implementation of the fully homomorphic encryption, and it has been a basis for all of the other generations of FHE schemes.
LTV, the second generation. So LTV is developed by Lopez, Alt, Tromer, and Vakunthanathan. And as you can tell, its name comes from the first letter of all the developers' last name. This scheme is also based on NTRU. I put a description about NTRU, which states an open source public key crypto system that uses lattice-based cryptography to encrypt and decrypt data. Now, it also can encrypt a message of only 1 bit, and it is one of only 2 schemes that isn't based on RLWE. So LTV is a multi-key FHE scheme, and it's also an alternative to dominant BGV, which is a key tech tool used to keep noise levels consistent during module switching. Also, it allows users to be able to upload encrypted data to the cloud, and the outputs of the data will be decrypted. BLLN, second generation. This scheme is based on NTRU. It is also considered an improved version of the LTV scheme. It was developed by Bose, Lauder, Lofters, and Nahirig, which name comes from the first letter of the developer's name. It is also one of only 2 schemes that isn't based on RLWE. So this is a slide of primitive functions of BLLN. I got it from a website, a PDF when doing research. Of course, the citation will be at the end. But this kind of gives some of the math element of the BLLN scheme.
In the next 3 slides, we will be going over the third generation of fully homomorphic encryption schemes. The GSW scheme, which was developed by Gentry, Sahai, and Waters. This scheme was a big step towards a complete and implementable fully homomorphic encryption. At the time in 2013, it was the fastest FHE, and it is based off learning with errors. Some features that it offers is having bootstrapping being optional. It eliminates the need for modular switching, and even though this technique does not reduce evaluation complexity as much as it would like, it does reduce the space complexity significantly, all the way from quasi-cubic to quasi-quadratic. In 2014, a year after the GSW scheme, FHEW, or FEW, was created by Dugas and Micciano, and is similar to the GSW scheme. This new technique brought in a new homomorphic operation known as the NAND, or not AND operation. This allowed for a dramatic decrease in the level of noise than any other technique. This new scheme also brought in a better refreshing of the ciphertext. These techniques will be explained in greater detail in our paper. GSW is really a conceptual simplification of FHE, and while it is a great improvement to existing FHE schemes, it is still too slow to be implemented. FEW was an even greater improvement, especially the bootstrapping technique. Compared to the GSW scheme, the FEW blew GSW out of the water. It would take around 30 minutes for GSW to compute the multiplication of 2 bits, and would take the FEW about 1 second to compute the same task. So because the FEW had such an improvement in bootstrapping, the overall efficiency was much better than GSW. Even still, it cannot be implemented into today's internet. In the next slide, Sebastian will be going over the 4th generation and fully homomorphic encryptions.
Thank you, Griffin, for the overview of the 3rd generation, and I will be covering the 4th generation. Firstly, the scheme analyzed is TFHE, which stands for Torus Fully Homomorphic Encryption, which came about in 2016 as an improvement over previous schemes, but is still based on GSW and its ring variants for ciphertexts. And if you're wondering, Torus is actually a number system, just like the integers, but it includes real numbers in the range 0 to 1, or any real number modulo 1. Additionally, TFHE offers some extra pieces of functionality for bootstrapping, including key switching and CMUX gates, which will be explained in the following slide. Now I'd like to introduce some of the upgrades that the 4th generation has to offer. One of those is the use of CMUX gates, which are quick and are used for improving speed and bootstrapping. They're just gates that take in 2 encrypted values as inputs and an encrypted bit, and as a result we return one of the encrypted values as output. Additionally, key switching, which is now an operation aside from multiplication or addition that switches the key used to encrypt the original message, as seen on the diagram on the right, where we convert an LWE ciphertext from one key to another LWE ciphertext with a different key. In terms of TFHE applications, there are a number of them. For example, it's used in cloud servers, e-voting systems, machine learning, and neural networks with several layers. Also used in multi-key encryption, which means we process ciphertext encrypted with different keys. And lastly, there is a TFHE library that is created in C and C++ and is available on GitHub, which implements gate-by-gate bootstrapping and circuit bootstrapping, and it continues to expand as more research is done. I'd like to provide a summary of what was discussed during the presentation today. Firstly, fully homomorphic encryption involves encrypting ciphertext that allows our servers to work with data but never directly with the data, since we always want it under layer protection. The operations permitted are addition and multiplication, and can be applied as many times as needed, while the noise is under a certain threshold. To reduce the noise, bootstrapping was introduced. There have been 4 generations of FHE, each improving on the weaknesses of the previous generation, introducing new schemes, concepts, and optimizing bootstrapping for time. FHE has many applications, including the Internet of Things, data science, neural networks, and cloud security. Lastly, I'd like to conclude the presentation with some thoughts on homomorphic encryption. Firstly, HTTPS protocol, as we know, is efficient for securing our online data, but With the number of data breaches in the world increasing and at an all-time high, implementing FHE is a necessity. Additionally, for the past 4 decades, we've seen homomorphic encryption evolve as a concept, with many schemes being born over the years, and has many branches that are studied up to this day. Overall, FHE must continue to be studied and implemented if we intend to keep our data secure, as the world of cybersecurity continues to expand. My team and I would like to take the chance to thank everybody for listening to the presentation, and we all hope you learned something very useful. Thank you.